hashing, uh, benefit of hashing, we just discussed, like you want to store all those informations, then what are the way out? Right, so I want to do all these operations in constant time, right? One way of doing that was storing everything, but it is a huge waste of memory. That's why we are trying to do it using hashing. Okay. So, as I mentioned last time also, this hash function, let's say hash function is basically a composition of two mappings. Right. What are those two mappings? One we call hash code map. And what is this? In general, these keys are not integers. Right. So what we do, this actually hash code map converts those keys into some integers. Right. For example, your roll numbers are sorry, your roll numbers are the keys, and this is not an integer, right? So you have branch codes also there, right? But for example, if I consider only the last two digits, right? Uh, or maybe just I can use, I'll just convert it into integer by skipping the alphabets. Right. For example, let's say if someone is having roll number something like this, right? So I'll convert it to just skip this M and A there, like 2, 3, 0, 1, 2, 4, something like this. Okay, this is how we can convert it to an integer. This is just an example. Let's see a few examples of this. Right? Okay, so that does what is the purpose of this hash code map? It actually converts these keys into integers. Right. Now see, these integers are from a very big range. This could be from a very small range, but in general, this is some kind of big range is there for those integers. Right. So what we'll do next, I'll compress those range of those integers. Right. So that's why we call the second component as compression map. Right. What is the purpose of this? Is integers that we have after this hash code map that gets mapped to something from 0 to m. Sorry, 0 to m minus a 1. Right? Because right. So in between this, it's going to map. Right. Okay. So this is actually, so here m is the size of the hash table. Okay. Right. So let's see few uh, examples of popular hash code maps there. So one hash code map is something you can think of as integer casting. Okay. So what we do, if we have some numeric type keys that are having 32 bits, right? I'll just interpret that one as a integer, right? So if the keys are of numeric type or with 32 bits or less, it can be interpreted as an integer. Right. So if we have a some code, for example, this roll number here, right? In my system, it's represented by a sequence of zeros and ones, right? So that same sequence of, let's say, this takes the size of this binary representation of this is something that can be fit that is fitted within 32 bits. Right. Now, those sequence of zeros and ones has some interpretations in terms of integer. Right. So I will interpret that key, that sequence of zeros and ones as an integer. Okay. So now what happens if if my keys are again numeric type, but more than 32 bits. So if they are more than 32 bits, so then what should I do? So it's not always better to give a concrete example, but as long as you are getting the idea, that's okay. Hmm? As I explained. So can you tell me what's the binary representation of this? It's not evident, right? So that binary representation, let's say, for example, it's 1 1 0 1 0 0 0. Let's say 1 1 1 0 1, something like this, right? Of length within 32, right? Less than 32 bits. So I'll convert this one. This is a binary sequence, right? What is the decimal representation of this? Right, so you know how to convert a binary to a decimal, right? So you convert this into a decimal number, and you will get an integer basically, not just any decimal. It's an integer. You convert this sequence into an integer, and that will treat as this conversion from this sequence of zeros and ones into integers. That is called integer casting. So I'll treat that one as an integer. Okay. Right. So now if I have something more than 32 bits, let's say a sequence of zeros and ones, right? Let's say it's 64 bit, right? So what I'll do, I will break it up into pieces of 32 bits, and so I'll get an integer out of this. For this, I have some integer. For this one also, I have some integer, right? And I'll add those things up. That will give me another integer. Okay. So this is the situation when we have a string with more than 32 bits. Right? I'll break it in chunks of 32 bits and convert them into integer and add them. Then again, I'll get an integer. Okay. So this is known as something called component sum. As the name suggests, you are treating them as components. Each component, you convert it into a integer and then add them up. Okay, so these are some like frequently used hash code maps that I'm telling about. Okay, so the third thing is kind of polynomial accumulation. So I'll tell you what it is. Right? So let's say you have the keys you are treating as just names of something. Okay. So these keys are basically coming from these are some strings of a natural language. Right? Okay. So what you do, you you take that one. Let's say, for example, let's say, right. So I have a key, something called Aman. Right? So what I do, I will take their ASCII values. Right? You know what are these ASCII values? ASCII values you take. So let's say I have, let's say A0, A1, A2, A3. Right. So these are the ASCII values of these characters. Right. You consider the uh, ASCII values of this, right, of each of these characters, and then you out of so consider these ASCII values as coefficient of some polynomial, and you convert this polynomial. So you construct this polynomial, right? Okay. So what would that polynomial be? So it will be like a3 x cube plus a2 x squared plus a1 x plus a0. Okay? This is you consider a polynomial in x, okay, and evaluate compute px for a for a fixed value of x. So you are going to get a uh, integer out of this operation. So generally we take these values. It has been seen that, for example, these values works really well for this polynomial accumulation method. Right? So in general, if you have a key with n characters, right? So each of these characters, you convert them as uh, convert them into ASCII code and treat them. So let's say their ASCII codes are AN minus 1, AN minus 2, and then all the way up to, let's say, A1, A0, right? So what you do, you multiply x to the power n minus 1 with this, x to the power n minus 2 with this, x with a1 plus this. So you compute this, right? And you will get an integer. When you compute this polynomial at, let's say, 33, then you will get an integer. Okay, fine. So these are some examples of your hash code map. Now let's move into some popular compression map that we can have. Some one of the most frequently used compression map is some kind. Uh, so what do we have to do? So I can treat this k as an integer now, right? So remember the purpose of this compression map. Integers, it will bring down the range of those integers into uh, within the range of 0 to n minus 1. Right. So we have seen an example. Suppose k is a integer, like can be very big integer. Can you think of a natural way of bringing it down to the range of m, 0 to m minus 1? Actually, we have used this before. Can you suggest any idea of bringing down that k within a range of 0 to m minus 1? It's actually very natural. So what you do, you divide that by m, divide k by m, and consider the remainder for this. When you divide k by m, then you'll get some remainder, right? And that range of that remainder should be within, this is actually within 0 to m minus 1. So you can bring down this range to this. Okay. So here you have to understand that this choice of this hash table size is critical. Why? Because suppose let's say I take a table of size this. So some so think everything is we are generally doing it in binary system. So suppose you have a binary number, let's say, and you uh, do it this way, right? You divide it by uh, m, right? Where m is some 2 to the power t. Can you tell me what would be the result of this? Then what is this h of k? This is nothing but this 2 to the power t, right? So this actually is the is the t many least significant digits of k, right? What is it? So basically, it's similar to something like when we have an integer, like Uh, yes, so I'm explaining what it is. So suppose I have this integer, right? I divide it by, let's say m, I take to be 10 to the power 4, right? What is the interpretation of k is this interpretation of this k dividing by m and taking the remainder? What does that mean? What will be the answer of this? K mod m. What would be the answer for this? Can anyone tell me? Hmm? Mod, not the so not 4. This answer will be 0139. This will be the remainder. This is actually so k mod m means like you divide k by m and get the remainder. This is the remainder that you will get when you divide k by m. It's this, right? So see, this is the last 4 digit of it, right? So the same thing I have just mentioned in binary terms. When you divide it by 2 to the power t, so this is an example of the decimal number system that I just said, right? And here I have just mentioned everything in terms of binary number system. When you have this k, you divide it by 2 to the power t, and basically that you by that you are taking the last t many. This t is the same as this t, right? T many least significant digits of k. So I hope you got it. So now the C, like when you have this range, so there are many numbers, so many keys you can think of that has the same last 4 digit, right? So in fact, there are, if I just take vary this, so actually it's like for each of 9 to the power 4, many, 9 or 10 to the power 4, many of this. Yes. Right? For this example, it's the last 4 digits. Last 4 digits because this is in terms of decimal number system, right? In this example. But what I said is like when you have binary number system, it's like last t many bits. Okay. Or last t many bits, significant bits. Okay. So as I'm pointing out that there could be many different key values that has the same last digit. So all of those under this completion map, all of them will be going to the same slot, right? So this probability of collision will be higher, right? So it's better to take m to be some kind of prime number, prime number, and m should be some prime number and also far from numbers of this type. Okay. Far from, let's say, 1, 2, 4, 8, 16, 32, 64. Right. So far from these numbers. Okay. So another way of dealing with this is I'll just tell you one more such idea of this. So Oh, generally, we do it this way also. I multiply k, first k with some constant a, where this a is constant within 0 and 1. Right? So I multiply this and take the modulo of this. Okay. So let's say A is something like 0.23. Right. So first I'll multiply k is an integer. Right. So I'll multiply k with this fraction value. So I'll get some decimal number. That decimal number may or may not have a fractional part. Okay. In fact, it will have. Right? Okay, may not have this fractional part. Also. Okay. Then what we do? We take modulo 1 of that. What does that mean? Modulo 1, some decimal number which has, let's say, this Ka turns out to be, let's say, 2793.6172. Let's say you have this as your K times A. Then what would happen if I do a modulo 1? You will get only the fractional part. So when I do this modulo 1, you will get 0.6172. Right. Right. And then I'll multiply this with the size of my hash table. So what would be the range of this multiplication? So and then what we did, I removed this part, 0, and then I multiply this with my size of the hash table. So this is going to be within the range of 0 to this. Uh, okay, so let's I should say this will be something like 0 to this value will lie within 0 to m. In fact, m minus 1, right? 0 to m minus 1, it's less than this, but it could be a fractional number, right? So to make it integer, I will take the floor of it. It's 0 to within 0, less than m, I can guarantee that. So to make it integer, I'll take the uh, ceiling of that, right? Okay, you understand? So this earlier, what we just did, we were dividing it by uh, m and taking the remainder, right? Now this time we can do it. We are doing a whole lot of jugglery with numbers and doing it. So most likely those type of problems that we had, for example, problem of m being some 2 to the power t, those should not occur here, right? So here the value of m is no longer critical, not critical, right? In fact, we prefer these type of values. M is 2 to the power t. Right? Why do I prefer such values? Because these are easier to compute. So manipulating, multiplying with m, right? That means you just consider the t bits of it. Right? Okay. Like you have to append few t many zeros to that number, right? Okay. But here the choice of A is critical. That first A, that the fraction that you, right? And it depends on the data set that you have. For different data set, you choose different A, and that will perform better. Okay? And one special thing, special number, we take it as the value of A, right? And it's a, you know what is this called? It's a golden ratio, right? So if you use this number, right, we called it appears in many places, right? So when you solve a Fibonacci sequence, right, you will get this number, right? So power of this, right? So when you take A to be something like this, then this is called, this hashing is called Fibonacci hashing. Okay, so you got it. So this, what is Fibonacci hashing? Fibonacci hashing is the spatial value of A. If you take this value, then this compression map or the whatever you use before it, this hashing is known as Fibonacci hashing. Okay. Any questions at this point? It's designing a hash table is more than an art. So it develops a practice. Okay, so it's still not clear why are we doing all these type of things, right? Um, so you'll realize these when you do some kind of practical programming, right? Practical projects when you do, right? So uh, that I cannot show you at this point, but I can give you some idea. So if you uh, try to maintain some data set, right, of size, let's say 10 over 10. Hmm. Let's say you have these many students, right, and you maintain their records. Hmm. And the operations that you will do, searching, deletion, and insertion, right? Then you'll realize that why this hashing is so important. Just by storing them linearly or some tree-like structure, that will not help, right? we want to store them in such a way that all these three operations should be doable in constant time. That is our main objective. Is this clear now? So it's I understand it's difficult to realize at this point, but if you can imagine dealing with this much of data, then you'll see. So just write a for loop. Okay, just write a for loop that runs from 0 to this much number and see how much time does that take in your system. Okay. And in fact, it's kind of a relatively small data set, 10 to the power 10. Okay, so let's come back. Now I'd like to talk about something called universal hashing. Right. So what is this hashing? So I have a data set. I want to map it to a hash table. So I have this data. I want to map it into a hash table. For this conversion, I use a hash function. Right? So what is a property that I want? It should distribute everything evenly. Right? It should not be the case that everything goes into the same slot. Right? That should not happen. That's not right. Okay. Suppose that you have decided to choose. So let's say the keys are some values. Let's say, for example, let's take this example. These keys are some values, let's say integer keys. Right? So say everything is a 10 digit numbers, 10 digit integer numbers. Right? These keys are a 10 digit integer number. That's a phone number, let's say, for example, this. Right? Okay. So now, let's say this is my data set, right? And you are using a hash function, something like this. H of k to be like k mod 100, right? Okay. And let's say, so what's the size of the hash table? Size of the hash table is, what is the size? 100, right? So all those integers, you want to convert them into the range of 0 to 99. Okay. Dividing by 100 means that. Dividing by 100 and getting the remainder, modulo operation, right? So all those, this hash table is having size now 100, 0 to 99. Right? Last two digits, basically. Correct. Now, suppose I know that you are using this hash function. And as an adversary, I'll try to construct a data set that will be very difficult for you to handle. Okay. So suppose these keys, I know that these are this type of numbers, 10-digit integers, right? But I didn't give you the data set, but I just told you that this is the type of data that you are supposed to handle, right? And you have chosen your hash function based on that information. You have chosen your hash function to be something like modulo 100. Right? Now I will give you a data set. Okay. And I'll try to give you a data set that would be very difficult for you to handle. Okay. So can you construct a data set of, let's say, size, let's say 10 to the power 5. So can you give me a 10,000 number? Sorry, one, let me do this 1 lakh, right? So those many numbers can you give me, 10-digit numbers can you give me? That would be difficult to handle for me. That means if I use this hashing, still I'll be doing something similar to unordered sequence. Any idea how to construct such a data set? Last 5 digit will stay in the hash table. Yeah, so not just 5. So I will give all those previous 8 digits differently, but I'll fix the last 2 digits to be 3 and 1. And I can put any numbers between, let's say here I'll have 9 different options. And for all of this, I have 10 different options. Right. So how many such different numbers? 9 to 10 to the power. So 8, 7. So these many different numbers I can give that has the same last 2 digits. And by that hash function, what will happen? The hash function that you have chosen, that will actually map everything, all of these many different numbers, it will map everything to the slot 31. Right. So, and so we have a calling collision. Then I'll be using chaining. So I'll list everything. Right. So I'll get a list of that big size. It's exactly same as doing some. Yeah. So what is the problem here? Problem is once I know that which hash function are you using, so I can back calculate and give the data set in such a way that all those keys are going to map to that particular slot, one particular slot. Okay, so here's the point that I want to make. For any choice of hash function, there exists a bad set of keys. Right? What do you mean by bad set of keys? Where all the keys are trying to map to the same slot. So what is the way out of this? So instead of using a fixed hash function, I'll create a set of hash function. Let's say capital H. And while working, we will pick one of those hash functions at random. Let's say in this collection of hash function, you have used, let's say, n of them. N hash functions you have. Now, if you choose any of these hash function, there's no way that I could know which hash function you have chosen, right? Then it will be difficult for me to choose to construct such a set of data, which would be difficult for you to handle. Okay. So you understand the idea of, have you understood the idea of this idea of universal hashing? This is what's known as this universal hashing. So this collection of this H here, this is known as, this collection of this is known as universal hash functions. So one result I like to mention that it's like there always exists existence of this universal hash function. You might be thinking that like how can I which hash functions I should be taken in the collection, right? It's actually difficult, right? But we can show that there exists a collection. Right? Constructing a collection of hash function, universal hash function is kind of difficult, but the existence is rather easy to show. Collection H of hash functions, or is called a universal hash function, such that for any randomly chosen hash function H from this collection, here's what is the thing. The probability of, sorry, uh, H of K1 is equal to H of K2, that probability is less than 1 by m. Right? What is this? So just uh, let me explain what I mean by this. So what is h of k1? So what is h? H is one hash function that I have chosen uniformly at random. Okay, that's a hash function you have chosen. Right. So what is h of k? The slot where this k1 is trying to be mapped. Right. H of k2 is the slot where k2 is trying to get mapped. Right. So what is this situation? K1 and K2 both are trying to be in the same slot, trying to get in the same slot. That's the collision, right? So it says the probability of collision will be one, at most 1 over m, the size of the hash table. It's quite a less probable. It's a recall our object like properties of good hash function. One of the property of good hash function was this probability of collision should be less. Okay. So understood this idea of this collision, universal hash function. Any questions till this point? Okay, so what I just said is like, uh, this is one result that you should know, that I can construct that, sorry, I can, but it's difficult to construct, but there exists a collection of hash functions such that if you choose any hash function from that collection, the probability of collision is at most 1 over n. Okay. Okay. So now let's explore another way of one way of collision resolution. No way of seeing that's by chaining. So now we'll see one more collision resolution technique that's called open addressing. Right? So here's the situation. So this time open addressing means that we are going to store. So earlier what happened in chaining, what happened in the hash table, we had only pointers to linked list. And the elements were actually stored, elements of keys were actually stored in the linked list. But this time we'd like to store uh, all the elements, all the elements are stored in the hash table. Right. This time I want to store all the elements in the hash table. So what is the requirement for this? Number of elements that I am storing. This is the data set, right? That n is the data size, right? Number of elements that I'm storing. That should be at most the size of the table, right? Table size should be, so if I'm storing 1,000 data, then my table size should be of at least of size 1,000, right? Otherwise, there's no way of storing them in this, in that table, right? Okay. And each table entry is either empty or an element. Right? So since we are storing the elements in the inside the table itself, so the cell that those table should contain the elements, right? But it may not, one cell may not contain the element. Okay, so the mm, any of those element parts. Right? So here we'll talk about something, a technique called linear probing. Right? So I'll tell you what this linear probing is. So I want to store. So let's say I would like to give explain this with the example. Right? Let's say I want to store these key values. Let's say 18, 41, 22, 44, say 59, 2, right? Let's say these 8 values I like to store, right? And I have chosen my table size to be, let's say, 0, 1. screen. Then I have 12. Right. So I take the table size to be, what's the table size? M is 13 now. Right? And I use a natural hash function. H of k will be k modulo 13. Okay. So this is the hash function. I want to store them in the table. So as usual, we are supposed to have, we might have some collision, right? Now, how we are going to resolve that collision now? So earlier what we used, you changed the content of this. So none of the elements were allowed to store in this table. Rather than that, we had a linked list hanging out of this, right? But this time we are going to store them in the table. How could it happen? What will happen? Let's try to do this. So can you tell me which slot should this 18 go? So I want to insert this 18 in the hash table. K is threshold constant, no K is the key. Yes. So I'll divide K by 13. I'll get 5 as remainder. So this 18 will come to this slot. Okay. So now where should this 44 should go? Where should I put this 44? In the second place. Why? 44 divided by 13. Yes. So if I divide 40, no, oh, okay. So this is 41, right? Okay. 41. Achha. Yes, 41 should go. Okay. So I just jumped at that time. So 41 should go to the slot 2, second slot. Yes, that I'll get remainder as 2. So then 22, where should it go? 22 should be coming to slot 9. Why 8? Dividing it by 13. Right? Right? Now comes 44. Right. So 44, if I divide 44 by 13, then I will be getting 5 there. Right. So 44 is trying to get in here. Okay. So, but this is the situation of collision. This slot is not empty. So what this linear probing, in this linear probing technique, what we do, we'll put, so we'll move through the table. We have reached this position, and now I'll move. So since if this slot is occupied, then the element will be inserted in the next slot. Suppose this is also again occupied, then it will be inserted in the next slot. I'll keep looking for an empty slot. Right? Suppose we come here. So where should I go if this is occupied? So I should be again come back here and check whether this is occupied or not. If empty, then I'll insert it there. You understand this idea? So 44 is now trying to get in the slot 5, but that is occupied. So I'll move it. I'll try to put that 44 in the next slot if that is empty. right? So the next slot is 6. Next slot is 6. This 6 is empty. So I can put 44 there. So I'll put 44 there. That's right. Okay. So then 59. Let's see, what about 59? 59, if I divide it by 13, I'll get remainder as 7, right? So directly, so there's no collision in here. 59 will get in there in the slot 7. Right? Now then 32. What about 32? Where should this 32 go? 32 mod 13. This one is 6, right? So this 32 is trying to get in here. So this slot is occupied, right? So it's not possible to push it here. Now I'll check the next slot. This is also occupied. This is not, I should not be putting it there. Now I'll move to the next slot. So now this I got empty slot. I'll put 32 there. Okay. So it will come to this slot. Yes. Okay. So in the similar way, where should this 31 go? Oh, sorry. 31 go. 31 mod 13 is, say, yes, 5. So now where should I put it? So 31 is trying to go in here. So this is not possible, right? So I'll check the next slot, occupied, next slot, still occupied, next slot, still occupied, next slot, still occupied. Then it will come to 10th, right? So here I'll have 31. Okay, so similarly, if you see like 73, where should it go? Uh, 13 dividing it by 13, you will get 8, right? So it will move to from 8 to 11, right? So 73 again. So in this way, I'm going to insert the elements. Okay, so you understand the technique here. So I'll you make use of this hash function. If that element is not there, I'll check the next slot. So why it's called linear probing? Each time I have to check, we have to probe whether I can insert it in the table or not. If uh, it's possible to insert, then I'll insert. If it's that slot is occupied, then I'll check the next. Okay. But now I hope this is clear to everyone. Now see, there is a problem with this is because it actually kinds of forms clusters, right? Since we always keep the next slot, right? There's a problem with this that it forms clusters, right? That's a one problem with this. Okay. So now what how can I search? So this is how this insertion will take place. Now how can I uh, uh, search for an element? Suppose I want to check whether 13 is or let's say uh, let's say I want to check whether 32 is present or not. Okay. So I have this table where I have this data. I want to check whether this 32 is present or not. How do I check? So I'll make use of this hash function. So, um, put the count ORI. Yes, yes, I think somewhat it's correct. Okay, so what is so suppose I want to search for it. So how does the searching take place? So I want to uh, search for 32. So what I'll do, 32 mod 13. So I get it like 6, right? So I'll first check this slot 6, whether there is whether the element is there in this slot, right? So then I'll check the next slot. This is also not correct. Then I'll check the next one. Then I'll get it. Sure, right? So I'll. Oh, so you have a question there? Okay, let me just answer. Just finish this searching and then let me answer. So I'll make use of this hash function. I'll look for this slot. This is not matching. So I'll look for this slot. This is not matching. I get it. Right? Okay, this is how we should proceed. Let's say I want to search for 33. Say, right? So what is this 33? 33 mod 13 is 7. Okay. So what I'll do, I'll check this slot. This is not matching. I'll check this slot. This is not matching. I'll check this slot. This is not matching. I'll check this slot. This is also not matching. I'll check this slot. This is also not matching. Then I'll see the next slot is empty. Can we infer anything at this point? So I can say that at this point, since by checking it linearly, I can see that I get to an empty slot that actually tells me that this 33 is not present there. If this 32 is 33 is present there, then it should have come to this slot. Think about inserting 33, right? So I'll check this one. It's occupied, this one occupied, this one occupied, this one occupied, this one occupied. Then I was supposed to insert it in this one, right? So same thing for searching also. So I'll checking everything, and then we get to an empty slot. That means that I have not inserted where that element should be because that element is not present in this. Okay, so how does this searching and searching take place? Is it clear? Any question about the searching? And all, if all slots are filled, but numbers remain, where to place? Okay, so is it possible to have all slots filled? There's no way that I can put it there. For this, let's focus on this assumption. What is this assumption? The number of elements that we are inserting should be at most the size of the table. Size of the table is more because I want to store everything in the hash table. So obviously, size of the hash table should be more than the data point that we have. Okay. Okay. Another question is if last one is filled, then where we have to add the, okay. So as I said, like if suppose this one is also filled, then what is the next slot? You check, you think this slot, this is a kind of circular list. So you again come back here, you check this one. If this is also occupied, go to the next one. Then go to the next one like this. You think this one, not just a single simple array or linked list, you think this one as a circular linked list. Sir, how did you? Yeah, so 12 slot. How do I make this 12 slot? Is it's like actually there are 13 slots. Thinking about the zero as well, right? Uh, Zero we have, so there are 13 slot. Is this 13 slot is coming because of this hash function? What is the hash function? I have chosen modulo 13. That means I'll divide whatever key I'll have, I'll divide it by 13, right? And whatever the remainder I'll take. So what's the range of these values? It can be 0 or all the way up to 12. That's why I have taken these many slots, 13 slots. Okay. So okay, let's come to this question, sir. जैसा आपने किया कि जिसका स्लॉट फुल था उसकी जस्ट साइड पुट कर दिया, बट इसका स्लॉट वो आ रहा है वो भी नेक्स्ट स्लॉट में ही चला गया. यस सर, तो हमने इसे 0 और 1 2 3 4 में क्यों नहीं रखा? Yes, so I'm not putting them arbitrarily. I should be following some process to insert those elements. कुछ एक process follow करना है, right? So it's not that wherever I find nearby, I'll put it there. It's not like that. So suppose I try to insert some element and it's trying to get in this slot. Then I see like in the right hand side is mostly filled. So I go to the left and insert it, right? But there will be a problem because when later on, when you are trying to search for that element, so you cannot make such a claim. So from this point, where did you go? You go it this way, or you did, we have gone to that way. Those decisions you cannot make at this point of searching, right? Okay, so one more thing, this is not complete yet, so there are a few things left here for linear probing, and one more thing we'll see in the next class is called double hashing that will also cover. um, but the point is there, this searching process is, I think searching is okay, right? But there will be a problem in the searching process that I'll disclose in the next class. But if you want, if you think about that problem itself. So I think I answered this question, isn't it? Is this question answered? Okay. Oh, you put it to ChatGPT and convert it in English, or also translated you use that. Okay, so I'll stop here. Any question? Yes, so like if I'm to, it will be difficult for me to take those lab classes, or as well as maybe I can take few tutorial classes also, but not at this point. But don't worry, I'll finish this syllabus. I'll cover completely, right? But I'll not be able to take the lab classes. But later on, if you want, I'll also take the few of the tutorial classes as well. Okay. So I hope whatever we are discussing in the theory class, it's you're getting. Is it? Okay. Okay. So it's good to know that. And if you have any questions, so each time what I do, I just recap the previous class. If you go through the lecture notes, I'll try to put it now. You go through the lecture notes. If you find difficulty, you ask me at the beginning of the next class. Okay. I'll try to clear your doubts. Okay. Yes. Yes. And happy Diwali to everyone. We'll meet after this Diwali then. Diwali, and after this chat, we'll meet. Okay? Okay. Okay. Happy Diwali. And bye for now.